before I go to lunch today, hopefully, or maybe this afternoon, but definitely today. And I'll post them along with the solution, the video solution that you can look at. If you have concerns about your test, please come see me. I'll certainly sit down and talk with you about it. The ones that have OXT next to them, those are from OpenStack. Just FYI. All right, guys, I forgot to bring my notes today. I'm just going to sort of... Yeah, bring it. Hey, hold on, guys. What'd you bring? Hey, guys. Oh, I reported last time. Thank you for asking. It wasn't as high as I'd hoped, but yeah, I don't ever give any statistics about the exams. But if you want to talk about your exam, then please come see me about your personal case. Yeah. Is that good? Yeah, Whitney. No, there's no curve. All right. Maybe later in the semester if I feel like the class is sort of behind. But for the first exam, I wouldn't have given a curve anyway. But it wasn't an 80% free. But it wasn't a terrible average either. Bryce? The final is cumulative, and so let me give you some bright spots on this. One, you'll have some extra credit along the way. I don't think that's even in the syllabus. We have to take a gen ed assessment, and you'll have various other things. I usually give about 20 points of extra credit, plus a few extra points at the end of the semester. All right, so that's one bright spot. The final is cumulative, but the final comes from your 4 exams, and so the average on the final is usually a little bit higher than the 4 exams. I take the questions from the 4 exams and I change them, kind of like I changed the OpenStax questions, and I might put different numbers or change the wording a little bit. Sort of the ideas that it's asking will remain the same. And so students, when they study those 4 exams, they tend to do better on the final than they do on the 4 exams because they've seen that material before. Other bright spots, the OpenStax, as I said, counts as an exam. Your class participation, that's 50 points, which is not insubstantial. And if you come to class, you will get the whole 50 points. There's no doubt in my mind about that. If you come and do the clicker questions. Okay, so there's not like every reason to have a long face, but some of you do have long faces. But take that frown and turn it upside down, right? Isn't that what they say? Okay. Any big plans for the weekend? Family Day is tomorrow. I'll be out there. We're going to make ice cream. The chemistry club is out making ice cream. I think they're making it every hour. It's liquid nitrogen ice cream, but it's just regular ice cream. And then Geomatics is going to be out. They're going to have some cool stuff with football, throwing football stuff. Are y'all at Boost this weekend? My wife is judging the Boost, so you can slip her an extra 20 if you know her. She might see your way. No, I'm joking. She's above all reproach. She's awesome, honest, all that. All right. We're going to look at projectile motion. And if you did well on the previous stuff, this is going to be super easy. But let me tell you that projectile motion is not super easy. That often students will struggle with it a bit. But it's really just taking our free fall problem and taking our constant velocity problem and fitting them together. And then we have a little bit of extra stuff that we have to do in there. So we'll spend some time practicing the problems. This is 2-dimensional motion. That is that we're going to be in the x and y directions. So we'll have an object that's moving in the x direction at a constant speed, and then we'll have an object that's moving in the y direction, not at a constant speed, accelerating by the acceleration due to gravity, and we're just going to fit them together. So instead of going up and down or side to side, it's going to go like this in 2 dimensions. All right, in the horizontal direction, AX, that's the acceleration in the x direction, is equal to 0. And by the way, now we need to be very careful with our accelerations and our velocities. So now whenever I have A, I'm going to have either AX or AY. And whenever I have v, I'll have vx or vy. And whenever I have v naught, I'll have v naught x or v naught y. And that'll be those particular quantities, a, v, or v naught, in the x or y direction. And then, of course, also we'll have position in the x and position in the y. So just be careful. We have an extra set of subscripts that we'll need to be very careful about making sure that we write them down correctly. Because depending upon whether we're dealing in the x or y direction, it'll be a little bit different. Ax equals to 0, and because the acceleration in the x direction is equal to 0, vx is equal to v naught x. That's just saying that whatever your initial velocity in the x direction is initially, that it's going to be the same. I have something traveling along in the x direction at a constant speed. No acceleration because ax is equal to 0. In the vertical direction, ay will equal to negative 10. All right, so we can have, this is just like our free fall problem, and we'll treat it very much like our free fall problem. Let me remind you with our free fall problem, which we had one on the test, an object goes up and comes back down again. There are a couple of key points on here that at the top, that Vy is equal to 0, T up is equal to T down. And those will be important points as we're going through 2D motion. The same way that we work the free fall problem will also apply now to projectile motion. And this is just sort of a, I don't know, a bonus for you. Do you know what angle is when we have a projectile, we have that projectile going at some angle. Do you know what angle will give you maximum range? 45 degrees, right? And we'll see that a little bit later, but an angle of 45 degrees gives maximum range. If you've ever tried to squirt somebody with a water hose, you notice that, if you start with a water hose at a shallow angle, it'll go like that. And then as you get up to a higher angle, 45 degrees, it'll go higher. But if you go above 45 degrees, like this, it goes down and comes back down like that. So there's a sweet spot at 45 degrees, which will give you maximum range. Try that with your water hose. Just start with a water hose and try to squirt somebody, and you'll see that the 45 degree angle, like this, gives you maximum range. Okay, so this graph sort of shows, or does show, how our velocity changes with time. And so our this vector right here shows our y velocity, the one that's pointing vertically. And so this is just like what we had with the free fall, that initially have a big positive velocity in the y direction. It gets smaller and it goes to 0, and then it gets bigger and bigger in the negative direction. So if I were to plot Vy versus t, it would look like this. That's what that graph would look like. And by the way, you can still see some more qualitative graphs of motion on the next exam. Likely you will, but as it relates to projectile motion, not just to free fall motion or just motion in general. And then if I look at the Vx versus t, what is the acceleration in the x direction? What is the acceleration in the x direction? Oh, she'd always forget. Oh, no, what is it? It's 0, right? It's not accelerating at all. Later in chapter 4, we'll see that's because there's no force acting in the x direction. But for now, we just say the acceleration in the x direction is 0. And so because of that, because ax equals 0, vx is constant. All right, and so that's why this vector is always the same length. That vx is always equal to v naught x. All right, so if I were to draw the v versus t graph for this, that's vx, it would look like this, just a straight line. And by the way, if I wanted to draw the x versus t graph, it's going to look like this. Sorry, that should be the other way around, x versus t. Okay? Because this line has a constant slope in the position versus time graph, the velocity is always the same. You know what I mean? All right. By the way, if I were to draw the y versus t graph over here, y versus t, it would start out with a big positive slope, go to zero slope, and then come to a big negative slope. So it would look like this. Big positive slope, zero slope at the top of the trajectory, big negative slope at the end of the trajectory. Okay, so that's sort of the outlay. And we'll look at several different projectile motion problems. You can sort of think of them in, I don't know, in classes, I guess. We'll look at the one where we'll look at a projectile motion where we have an object that starts at some point and ends at the same height. So we could have something like that. We could also look at one where we have an object that starts at some height and basically just goes through the second half of that trajectory. Mostly those are going to be the ones that you're tested on, but we could have other scenarios too. And in fact, I could take some of these other scenarios and we'll work through some and make them simpler for the test. Where, say, for example, I have this one where it starts at an angle and travels down like that. We worked variations of those problems in the previous chapter, except now we're just adding in that X motion. In fact, you'll have a lab soon, I think next week, depending on how your schedule falls out, where you're doing projectile motion. And you'll work through all three of these scenarios, or at least you'll work through the second one and the third one. The first one we're going to do in class a lot. Okay, dokie? All right. Oh, what is that? Oh, that's the last page. Sorry. You'll get an equation sheet probably on the third exam, by the way. That'll be it. Okay, let me show. Ooh, let me see if I have. Ooh, I do. Okay. Show you a little video. Y'all did this in lab, but I like to show it because it really does illustrate this motion. This is a video from, it was a home video that somebody had made, but they made it after their house burned down, and when their house burned down they lost all their home videos. And so they were trying to recreate some of their home videos. Oh, that's funny. Here it is. Y'all have done this in lab, or many of you have, where you analyze the video. It's really powerful, actually, to be able to take a video of motion and then be able to interpret things about its velocity and acceleration. So I have a student right now that's working on, he's trying to develop a new way to assess athletes, and so he's using the software to determine the force that they do when they do the vertical jump and the broad jump. And we'll get into that later in the semester, but it's pretty powerful. So I'm going to insert the video here. Couple of things I want to show you as we're doing this about the slope of the graph. If you're not in lab, if you haven't seen this, when you have the video, you just go to the frame that you're doing. Let's see, we'll do this one. This was a free throw shot. And then you can go frame by frame. You see the basketball sort of going through space just as it leaves its hand. You want to set your coordinate system. So we're going to set our coordinate system right here. And then we want to set our scale. I'm going to set my scale. This tells the software a pixel is equivalent to what distance. And so this guy, oh, how tall is this guy? In meters, how tall is he? He's about 2 meters. Yeah, he's pretty tall. So about 2 meters. So that gives us our distance. And then we just click out point by point and we track that basketball. So think about, what is the y velocity doing? Is the y velocity increasing or decreasing as it goes up? It's decreasing, right? Because the acceleration is in the negative direction. And these points actually will trace out the position versus time, because each each click is equivalent to about 1/30th of a second, which is sort of the time resolution of your cell phone camera. All right, we'll stop there. All right. So now if we look at this graph, we have the red dots. The red dots refer to this is position versus time. The red dots refer to the x or the y velocity. That's going to be your x velocity because ax is equal to 0 for those. And then the blue dots, that refers to your y velocity. And in fact, we can look at the slope, or your y position. The slope of this is initially big and positive. This is at the top of the trajectory, where the position is 0. And then over here, our slope rather, gets negative and bigger. We can also show some velocity graphs here. This is our x velocity. It just sort of has scatter, so our x velocity is constant, and then our y velocity is here. Now, what should be the slope of our y velocity graph? What do you think should be our slope of our y velocity graph? Now, notice we have it here. It crosses at 0. This is the top. We initially have a big y velocity, and then we have a small y velocity. All right, it goes to 0, and then it gets bigger in the negative direction. What should it be? It should be -10. And so we can measure that. We've sort of done a shoddy, or quick and dirty here, but let's see if our slope, I can measure my slope here. It's -14, so maybe we had our scale a little bit off. But our slope here should be -10. So let's go back to the notes there. You should have that graph. Just want to point out a couple of things. This represents our x position, big positive slope. Or excuse me, this represents our y position. Here, Vy is equal to 0. This is our Vx, and it's going to be a constant value because Ax is equal to 0. Let's see. And then if I look at my Vy and Vx, this is my Vx graph. We're plotting the velocity. And then this is our Vy. And the slope of this line is equal to -10 meters per second squared. That's our g value. Okay, so we'll see some more graphs of this type of motion, but I just want to keep in mind that our acceleration in the x direction is 0, and our acceleration in the y direction is that -10. And then all the answers are like what we had before. Rebecca, are you holding that up for me or for Ethan? For Ethan, okay, awesome. Okay, guys, let's see what's next. I don't know what's next because I don't have my notes. Let's do this, and then I'll hand back the rest of your exam. In fact, I'm going to go